let's take a look at how Cython plus actor system can be used to do some work in parallel. So we're here in a Cython plus environment, so it's a Python 3 virtual environment in which we have already installed Cython plus and in which we have downloaded the standard library and the runtime for the actor system. To reach this step again, please refer to our Getting Started video. And so I have also begun a small program for actors. In which essentially we define a measure method we'll call from Python, which starts a scheduler for the actor system. This scheduler can take an argument defining the number of system threads it will use. So the scheduler's job is to schedule the actor tasks onto a given number of fixed number of system threads, and we can configure what this number is. So this will allow us to essentially see how our program scales up when we increase the number of system threads it runs on. Then we do some time measurements, and in the middle we haven't done it yet, we'll define launch some actors and make some work happen. And then we'll call scheduler.join, which tells the scheduler to wait until all pending tasks are done and there is nothing left to do. And then we'll just print the real time and the process time, and we'll deduce some approximation of the parallelism achieved this way. So the real time is essentially the clock time that elapsed during the execution. Of course, this is somewhat approximate because we're not running a benchmark on a machine dedicated to it that doesn't do anything else. So this is not a precise timing of the actual execution time of the program. And then there's the process time, which is the amount of time that has been spent on actually running the program. So this means when another process runs, that time is not counted. And also when multiple threads run in parallel, each thread, the time for each thread is counted independently. So if two threads run full time for the whole time of the execution, the process time will actually be twice the real time. And this means that essentially by dividing the process time by the real clock time that elapsed, we can get some idea of how much work was done in parallel. Let's define some actors. So in Cython Plus, an actor is actually a normal instance of a normal SIP class, and SIP class is our child-free class system. In fact, an actor is just an instance of a SIP class that happens to be in a specific state, an active state, in which it behaves asynchronously, and calling a method on it will only store a message in the queue for this active object to be run at some later point when the scheduler runs it on some thread. Let's define our SIP class. We'll call it tree because we're doing a tree of actors essentially. Although actors are normal SIP classes, we still need to add this activable keyword. So this does not mean that instances of this class will be actors. It means that instances of this class may be activated into this active state. The reason this is not the case by default for every class is just a matter of optimization to avoid generating the code for this asynchronous behavior when it's not needed. So our tree will have a list of children. So like this. Oops. So every element in this list is itself an instance of the tree class that happens to be in the active state. That's what this active keyword here means. So let's define an init method. And first we need to configure the mailbox for this actor when it's in the active state. The reason this is also something we need to do is because the actor system in Cython Plus is meant to be customizable by the user. And so this is one of the customization points in question. So for more information on this, please refer to the introduction video to the actor system. So now let's initialize our children list. Here there is a small issue we need to work around. So ideally we would want to write this. So just call the construction for the list. But because these are relatively recent features, the parsing for this expression doesn't work. So the parser struggles with this expression due to the active keyword here. And so to work around this, we can put the new keyword which resolves the ambiguity. But if we do this, then the constructor is not called. Well, the constructor is called, but the init method is not called. So the memory is allocated, but the init method is not called. So we would need to call it manually, like this. But there's also another way. We can also just define an alias for the list of active trees. So let's call this the children type. And if we use now children instead of this explicit list, we won't have this issue with the parsing of the constructor call, and so we can just do it this way. Perfect. And now let's define a method to build a tree of actors. So build tree, and we'll make this customizable. So it will take an argument for the degree of the tree, so the number of children every node has, except the leaf nodes, which don't have any children, and the depth of the tree. So if the depth is 0, there is nothing to do. So, and if it isn't, let's build the subtree. So let's build all the children. So each child is itself an active instance, so we need to activate an instance of the tree class. We need a consume keyword here to guarantee that the child active instance, more specifically the child reference, is the only way to access any of the internal state of the tree created. So in other words, we want to make sure that there is no way to access the internal state of the tree, so no reference to the tree object or to any of its internal state that doesn't go through the actor, because that would mean we could modify its internal state synchronously in some thread and at the same time asynchronously in the actor thread. And that would not be thread safe. We want only the actor to have access to its internal state. So this child actor will tell it to build its own subtree. So the same degree, but less depth because we're already building the children. And there's one thing more when we make so this is an asynchronous method call on the child active object. When we make an asynchronous call, there is an additional argument at the beginning of the argument list. That is another customization point for the actor system in Cython+. It's meant to be an object, a sync object that can be used to modify the behavior of the asynchronous call, so reschedule it or wait for some synchronization before actually running it. But this is not needed for now, so we can just pass the nil argument. And let's add the child to our list of children. There. And we can already compile this, but let's first create some actor to so we'll create a root for our tree. Again, it's an actor as well. So make this once more. And we'll tell the root to build its own subtree as well. And in fact, let's make this something that can be configured from Python. So the degree and the depth. Yes. And let's compile this. Oops. Made a small typo. Up. And let's launch Python and import our extension module. So from boom, and now we can launch our method, and we'll see some timing prints out. So for starters, let's use one system thread, and we'll create a tree of binary tree of degree 2 and of depth 10 for now. Let's try this. So yeah, let's increase the depth a bit, maybe 15. Yeah, so now it takes a bit of time. So we'll see the parallelism achieved is 1, which is to be expected since we have one thread. Let's see what happens if we increase this to 2 threads. So it scales up to almost 2 parallelism of 2. Keep in mind this is a bit approximate anyway, but it's a good indicator that that essentially we've increased we've balanced the load on two threads. But you'll notice something a bit weird. So it looks like it's good and we have twofold execution, but actually the execution time has slightly increased, and in fact more than slightly. It has increased by a factor. So the whole process time has increased by a factor of 1.5. So it was 2 and now it's 0.3. So the fact that we speed up is somewhat balanced by the fact that overall it's a bit longer. Let's see what happens when we use 4 threads. So we're still scaling up almost to 4, 3.6. But again, we're losing some of that speed up on some overhead of the actor system. So the parallelism is 4, but we're not 4 times as fast as we were at the beginning. In fact, we're not even half as fast. originally the hold time was 0.2 and now it's 0.12. So yeah, some overhead is going on here, and let's increase this to 8. And so the parallelism is there. We're scaling up to close to 8, 7, close to 7. So might be some small inefficiencies here, but we're still only barely twice as fast, not even twice as fast as we were with one thread. And in fact, the whole execution time is 4 times as long as it was. So the whole process time is 4 times what it was when there was only one single thread. So basically, we're going 8 times as fast, but doing 4 times more work. So we're only speeding up twice. So there is a scaling issue here. Let's try 16. So again, we're really using our 16 cores. There is well, almost, but up to 14, but it's not bad. But the process time is now even bigger than before, and we are a bit more than twice as fast as we were with only a single thread. So we are using 16 threads, and we're still only twice as fast as we were at the beginning. And in fact, if we speed up to 32, the same issue still remains. We're barely twice as fast, and in fact, we're a bit slower than we were with 16 threads. So the scaling doesn't really follow. And that is because in our program, the actors are not doing much. So basically, all an actor is doing is sending messages to other actors, and that's it, appending something to a list, and that's all. So the ratio of time spent doing something in the actor as opposed to time spent communicating between actors is not very good. And so this shows that there is an overhead to actor communication, and this overhead does go up a bit when there are more threads. And so to make it worthwhile to use actors, our actors would have to actually do some work, and the more work they do independently of communicating with other actors, the more it's worth it to use actors. So to simulate this, we'll write a small method to simulate some work. So let's call it X. So what it'll do is it'll compute the this function will be no GIL, so work without the GIL. It will compute the power of 2 to the power of n in the worst way possible. So so assuming this is not optimized by a good compiler, to protect against this, I'll add the volatile keyword here, hoping it helps a bit. But assuming this executes as seen here, the computational complexity of this method is 2 to the power of n. So it takes 2 to the power of n work just to compute 2 to the power of n, which is the dumbest way possible to do this. But it will allow us to simulate some work. So let's add a work value to our class, and when building the tree, let's add a work argument, and let's compute 2 to the power of the work argument. And so yeah, so this will allow us to tweak how much time is spent inside this actor doing work. And yeah, we'll see how it goes. So let's add this as an argument to the Python method here. this. And also let's make sure we propagate it to the children here. Yeah, and then let's compile again and see what we get. This function needs a return value of type int. Otherwise, Cython plus assumes the return type is a Python object. So let's again go in Python. Import our measure function, and let's run it again. So as before, let's start with one thread, binary tree with degree 2, a depth of 15, and let's start with a work of 0. So this is the same as we had before. And we get sensibly the same results. And if we scale up to, let's go straight to 16 just to go see again the results we had before. In fact, we're not scaling up fully to 16 anyway. Depends on the execution. But we are doing 8 times as much work overall as we were before. So we're only having a twofold speed up. But let's see if this remains true when we increase the work. So let's start with a work of 10. So we'll compute 2 to the power of 10. So this is some execution cycles. In fact, takes a bit more time, not that much more time. So we'll see if it really has an effect. And if you go back to 16 now with this amount of work, it's not really better than it was before. So we're still only getting a twofold speed up. Let's increase this to 15. And now, so now we see we really have 10 times as much execution time as we had when the work was 0. Let's use this on 16 threads in parallel. And now we see that the execution time, the real time, has been divided by 10. So we're getting closer to our goal. So this is good news. Let's increase a bit again, maybe to 18. Yeah, that is some time. And let's go to 16 threads. And now we're quite good because if we take the real time it took to compute to work with one thread and the real time it took to compute it with 2 threads, we get a speed up of almost 15. So this is quite good. Let's see how it goes with 32 threads. So probably not as good, but now the real time is 4.91. We're getting a speed up of 21. So still some room for improvement, but we're going in the right direction. So what we're seeing here is that the more the actor system is biased towards work rather than communication with other actors, the more it's worth it to run stuff in parallel. And this is actually a general rule of concurrent design, but it's maybe particularly the case with this actor system where there is a real overhead to communications, because sending a message to another actor implies allocating some memory to store the asynchronous method and storing it in a queue. So the queue also needs some memory to store the data, and then scheduling this into a queue of workers that have work to do and running it at some point, and all of this implies some synchronization and even some overhead just from allocating memory. And even allocating memory, in fact, on a multi-thread system implies some synchronization for competing access to the memory, depending on the allocation strategy. So yeah, so this is a good way to get a feeling for our actor system. That's all I want to show you. Thanks for watching.